Okay, so we should start with our pieces of advice. And the first two are very familiar. Do problems because, well, there's 7 of them on the test, and you want to make sure you can do them. And there's this sort of convention that sometimes you feel like, as long as I'm in the room when math is being done, I am learning math. But that's not quite how math works. See, math, you got to learn how to think and how to do. And so, yes, being around people doing math can be a helpful environment, but only when you yourself are actively engaged. So that's why we want you to do problems, not just look at problems, not just watch videos of problems, but actually do problems. Take care of your health. Make sure you get plenty of rest, plenty of sleep. The goal is not to show up to the exam physically and mentally exhausted. That's what should happen at the end of the exam. At the start of the exam, you should be awake and energetic and be like, I am ready to tackle these problems. So that's what you want to make sure you do. And of course, as we say before, health includes mental health. If you need to go out and take a break, scream into a pillow, that's fine. I don't encourage you to do that during the exam, but as you prepare for the exam, whatever you need to do. There's this last thing I want to say is when we graded the first exam, at least when I graded the first exam, so I graded the last problem on the first exam, and time again, I would grade the problem and I'd be like, what in the world are you doing? People would do all sorts of stuff except the thing that was asked. And you might say, well, how do we know what was asked? Well, in that particular problem, we actually underlined, we didn't underline, but we italicized the words, the tangent line. And many people didn't even look at the tangent line. So you need to understand when to apply a tool. It's not just enough to say, I have this cool tool, and I haven't used it yet, so I'm going to use it. There are many cool tools that we've learned, and not all of them will show up on the test. Make sure you know when to apply a tool and that you're applying the right tool. It's not enough to just fill a page up with computations. You want to fill it up with the right computations. So, 14 problems, and we might take a break halfway through. Probably will take a break halfway through. Well, let's begin. Okay, so the first problem, we get to sort of channel our inner artistic passions. We're going to draw. In particular, we're going to sketch the domain of the following function, log of y minus x minus 3 squared over the square root of 9 minus y minus the square root of 3 minus x. Now, if there is a problem that says draw, you will see something like what you see here, which is you'll see a grid. We will give you a grid. And that's because we want to make sure we can grade easily. And it's much easier to grade when you all have the same grid. In fact, we're going to give you 2 grids if we give you a sketch problem. One for practicing your answer and one for your actual answer. So don't worry about whether or not you're going to need to draw a grid. Now for domain, whenever you see a domain problem, you say, okay, where are the possible problems? You just want to avoid that. And the answer is there are 3 possible problems. Divide by 0, that's bad. Or square root of a negative, that's bad. Or natural log of something which is less than or equal to 0, that's bad. So those are the things we want to avoid. So as long as we avoid those things, life is good. So essentially our domain is, where don't we have those problems? So you go through these one by one and you tackle them. You say, all right, we're going to figure this out. Now, a couple things pop out pretty quickly. We see these square roots. So, for instance, we see that, okay, since I have a square root of 9 minus y, it better be the case that 9 minus y is greater than or equal to 0, or y is less than or equal to 9. I bet you this grid is not correct. But, well, we'll fix it in a second. All right. 3 minus x similarly has to be greater than or equal to 0, or x has to be less than or equal to 3. Okay, so there are some conditions. Y has to be at most 9, x has to be at most 3. The natural log of 1 minus x minus 3 squared, well, that tells us that y minus x minus 3 squared has to be positive, strictly positive, because I can't take a log of something that's equal to 0 or less than 0. So this becomes y has to be above x minus 3 squared. All right. And now, what's our last thing here? Well, the last thing is we have to be careful in that we can't divide by 0. We haven't talked about that one yet. So we say, okay, well, when do we divide by 0? Square root of 9 minus y minus the square root of 3 minus x would have to be equal 0. So rearrange. That becomes the square root of 9 minus y would have to be equal to the square root of 3 minus x, which would happen if 9 minus y were equal to 3 minus x. So that's something we can rewrite. And if we do rewrite this, we can solve for y, because this is a line. That would say that y is equal to, let's see, what would it be? X plus 6, I believe. Okay, so those are the things. So here, that's when we get it to 0th number. So we want to make sure y is not x plus 6. Now, of course, we can see our picture is not going to work here because our grid was not properly scaled. So we're going to rescale our grid, 3, 6, 9, 12. Don't worry. We check the problems more carefully on the test than we do on the review. All right. So here we go. There's our problem. Now, before we fill anything in, we'll do a rough sketch over here and see what we have. So, y has to be less than or equal to 9, so we'll sketch the curve y equals 9. So we're below this curve y equals 9. X has to be less than or equal to 3, so we'll sketch this curve, x equals 3. And so right now, we know that we have to be below 9 and to the left of 3, so we have to be in this part here. We're also told that y has to be greater than x minus 3 quantity squared. Now, if you sketch y equals x minus 3 squared, what shape do you have? Parabola. What have you done to it? Shift it which way? To the right or to the left? To the right. In fact, it turns out that the parabola is going to hit at x equals 3. Now, I'm drawing it with a dotted line because I have a strict inequality. And which side do I want? Well, do I want to be above or do I want to be below? I want to be above. Okay, so now we're starting to sort of get a pretty good idea of our shape. So, we're almost there. What's the last thing that we have to nail down? Well, we haven't talked about y is not x minus 6. Sorry, y is not x plus 6. So y equals x plus 6 would be a line. So I don't want to be on this line. Avoid this line. Yes? No? Okay, so now I'm ready to draw the picture. Say, okay, well, I want to make sure I avoid that line, so I'm going to sketch that line in. So here we go, sketching in this line. I'm going to draw it dotted. So this is y equals x plus 6. It's good if you're going to draw a picture to label the curves, just so you know what's going on. Y equals 9, and I want that to be solid, going from 0 to 3. X equals 3, and I'm going to have that be solid all the way down until the bottom. And then I have this parabola that's going to be dashed. Okay, so that's our curves that come into play, and I'll label these curves here. Again, this is y equals 9, x equals 3, and y equals x minus 3 squared. Now, there's a couple of questions. What about the corners? Well, here's the thing. If it fails in anything, it fails. So, this corner fails because of the parabola, so it's an open circle. This other corner also fails because of the parabola, so it's an open circle. And this corner fails because of the line y equals x plus 6. So it's really close. See, it's a solid line, and it's a solid line, but yet at that corner it's open. So you want to make sure you get the corners in as well. And then, of course, for full credit, you got to make sure to indicate by marking where you include with shading. So if you do have to shade, make sure you shade. So this is an example where you would include the domain by shading it. So that's the answer. That's what the domain of the function turns out to be. All right, well that's good. Now, you might start wondering, what kind of curves will we expect you to be able to draw? And the answer is lines, circles, and parabolas. That's what we'll expect you to be able to draw. Maybe on a day, y equals 1 over x. But these will be functions that are fairly straightforward. There's a question.
I was just going to ask, do we want to put an open circle on the intersection of the parabola and the linear line as well?
Well, it's already implied to be an open circle because of its being dashed. It's essentially, it's when the lines come together that you might have to say. So oftentimes the question of when do we include a circle, when do we not, is, well, what if it happens when two lines come together, and like one's a solid and one's a dashed? And the answer is, if any one of them is dashed, it's out. It's out. You know, as the saying goes, on one curve you're in, but on the next curve you're out. So you're just out. All right. So we channel our inner artist a little bit more with number 2. Sketch and label the curves, the level curves, for the function z equals 4y over x squared plus y squared plus 1 for the values, or if you like, the heights of 2, -1, 0, -1, and -2. So level curves are when you set the function equal to a value. So we're going to take, this is our function here. This is our f of x, y. And we're going to set it equal to these 5 different values. And as we do, we're going to get these different curves emerging that are curves in the xy plane. So we'll set 4y over x squared plus y squared plus 1 equals 2. And if we rearrange that, we can say that if I divide by 2 and multiply by x squared plus y squared plus 1, this is the same as x squared plus y squared plus 1 equals 2y. Or x squared plus y squared minus 2y plus 1 equals 0, which is x squared plus y minus 1 squared equals 0. Now, that's kind of an interesting curve. What does that curve look like? It's a circle, is it? It's a single point. You can think of it as a circle with radius 0. So where is this circle at? Well, or where is this point at? The answer is that x equals 0 and y equals 1. Because if x squared plus y minus 1 squared equals 0, you need x equals 0 and y minus 1 to be 0. So what we get is a single point, and we'll label that with a 2. Okay. Now we'll do the next one. And all these are going to be the same process. So if it starts feeling like, wow, very repetitious, it's because it's very repetitious. You set the function equal to 1. Again, I'm going to multiply. So we get x squared plus y squared plus 1 equals 4y. Or x squared plus y squared minus 4y, and I'll leave a gap, equals -1. What should we do here? Complete the square, so we need to add 4. Add 4 to both sides. And so we're going to end up with x plus y minus 2 squared equals 3. So what is this? Well, it's a circle. Where's the center? 0, 2. So the center's at 0, 2. That's not part of the curve. The radius is square root of 3, which we don't have to know exactly. Square root of 3 is somewhere between, you know, it's between a little bit. Let's see, what's true? Well, it's bigger than 1. It's less than 2. Okay. So it'll be something, if here's my center, it's roughly, say there, and then we just eyeball. Look, we're not going to test you on, did you go out and get a protractor and bring it with you to the exam. I think protractors are allowed because it doesn't have any technology, but you don't need to be very precise, just something roughly like that. And now, so that's a level curve, but remember, you want to label, so we put a 1. All right. Next, well, probably I'm very looking forward to this one. 0. 0 is always a good one to work with. 4y over x squared plus y squared plus 1 equals 0. What does that say? Y equals 0. So that is the x-axis. So we're just going to label that as a 0. And then the rest are very similar. So this is what you do. So there's not much to this problem. It's just be patient, work through it, and everything works out fairly nicely. So again, I apologize. I'm not saying much commentary here, but that's because this one doesn't really need much commentary. You'll see it's really the same. The only thing that changes is the center of your circle is not up here, it's down here. It's almost like it's the mirror image, because it turns out it's the mirror image. So that's a good reason why it's almost like the mirror image. And again, this is -1. And if you go for your last one, there we go, 4y over x squared plus y squared plus 1 equals -2. And ... you'll get x squared plus y plus 1 squared equals 0. And so you'll end up with a single point here at -2. And that's it. Those are our level curves. Okay. So for this process, it's really just a matter of set your function equal to your number, solve for your curve, and then be careful with the picture. Again, you're going to have a spare grid to work with. And we're going to give you curves that you're familiar with. So there's nothing too surprising. All right, number 3. Oh, this looks good, because this has multiple parts. So, evaluate the following limits. So, A, B, C. Well, let's do them in order. We'll see what they become. Now, for the first one, we see, okay, we have sine of xy over x squared plus y squared. Now, when you see this limit, what do we think of? Well, we want to think of saying, if it's not obvious what to do, and because of the sign, it's making us nervous. It's making us nervous. So we want to think a little bit before we jump into this right away. So one thing we can do is we can say, well, let's approach it from a couple of different directions. What's some convenient directions to approach from? Okay, along the axis. So suppose we go along, say, y equals 0. Then what we get is this becomes the limit. Well, just there's only an x involved. And what I'm going to do is I'm just going to plug in y equals 0. And it becomes sine of 0 over x squared plus 0 squared. Well, that's sine of 0. Hard to recover from because that's 0. So we get 0. In fact, along the axis, either x equals 0 or y equals 0, the top will always be 0. So along the axis, we always approach 0. Is there something else we can try? Y equals x? That's a good choice. Y equals x. And so what we can do, now, you can do it either say, okay, replace y by x, or you can say, let's replace both of them by t. It's the same effect. If we did that, we get sine of, say, x squared over x squared plus x squared. Well, that's not immediately 0. It might still be 0. I could write this as 1/2 sine of x squared over x squared. Well, how do we figure out what that is? Well, if you know calculus, which we hope you do, because you're in Calc 3, you might recognize, hey, this is like sine of stuff over stuff. And we know that sine of stuff over stuff goes to 1 when our stuff goes to 0. That's what it's doing. So it goes to half. Now, if you didn't know calculus, you might say, but I know a little bit of calculus. I know l'hôpital. L'hôpital, mon ami. And you could be like, okay, take derivatives of the top and take derivatives of the bottom until you get something which is not 0 over 0, and then you'll end up with the same thing. So, okay. So it's a half. So what's our conclusion? Yeah. So for part A, the limit does not exist because two different values depending on approach. It's good to write down a short justification. Now, if they ask you to justify it, definitely justify it. If they don't ask you, at least make sure that the work makes it clear that you did something. Don't just say doesn't exist. Like, why? We want to know why. In fact, that's a good rule in calculus, is we care a little bit less about the answers and a little bit more about the process. We want to make sure you know the process. The answers are just a bonus. Okay, for part B, limit as xy goes to 0 of xy sine of 1 over x squared plus y squared. Now this is kind of curious. If you think about what's happening with this, see that 1 over x squared plus y squared, what's happening to that expression as we get close to 0, or close to the origin? It's getting huge. So what's happening is this is just wildly oscillating. So that's a bad thing for limits. But while it's wildly oscillating, what's true about how it oscillates? Because it's sine, it's always between 1 and negative 1. So it might be going up and down a lot. So it's like the sine 1 over x. If you ever remember the sine 1 over x, you know how it goes as you go towards 0. It starts doing, ah! Okay, it doesn't have to make a noise, but that's what it's thinking. And so it's like this curve, but if you spun it, because there's this nice rotational symmetry of the curve. So that it's going up and down a lot near the origin. But while it's going up and down, the sign always stays between negative 1 and 1. Now the good thing is it's a bounded part that's behaving poorly. So we say, well, the bounded part is behaving poorly. What about the unbounded part? Well, how does xy behave? It's going to 0. So if you have something which is going to a small number times something which is bounded, when you combine those together, what's the result? The result will be something small. Now the way we make that more concrete is we say, let's do a little bit of a squeeze on it, or sandwich, depending upon what type of thing you like to call it. And what you can say is sine of 1 over x squared plus y squared, because it's between negative 1 and 1, when I multiply it by xy, the largest it could ever be is the size of whatever xy is. The smallest it could be is the negative of the size whatever x times y is. And now we say, well, that limit goes to 0, and this limit goes to 0. And these are here when we're talking about the limits as x, y goes to 0, 0. So if these are going to 0, what's true about the part in the middle? This also goes to 0 by squeezing. So when you apply the squeeze, the key is find something above and below. Essentially you say, what's the part that's bad? That's between negative 1 and 1. Then everything else, what does that do? Okay, so that's part B. So the limit equals 0 by squeeze. All right, now we get to the harder one, part C. Find the limit as xy goes to 1, 1 of sine of xy over x squared plus y squared. Well, how do we handle that one? Yeah, you should always plug in. That should be your mantra. What happens at 0, 0? We should have been plugging in before. Of course, we plugged in before, we get 0 over 0. Here we get like 1 over 0. Like, that looks terrible. So the thing is continuous, because these are built from continuous functions, so it can plug in. And if they ask to justify, that's the justification, is that it's continuous. So the limit is sine of 1 times 1 over 1 squared plus 1 squared, which becomes 1/2 sine of 1. All right, that's everybody's favorite limit problem, is to just plug it in. Just plug it in. All right, number 4. So we're going to find A and B so that the planes z equals x plus y minus 2 and z equals 4x minus 2y minus 14 are both tangent to the surface z equals 1 over ax squared plus 1 over by squared. So we have this surface. It's kind of, well, if A and B are both positive, it'll turn out to be kind of a bowl. If they're both negative, an upside down bowl. Or if one's positive, one's negative, it's going to be a saddle. So we have this surface. We're not quite sure what kind it is, but roughly speaking, it's some sort of quadric surface. And we're trying to find A and B so that we have these two tangent planes. All right. So the question is, well, how do we do this? Well, let's think about it. Now, these are our tangent planes. In fact, they've given it to us in a very specific form here as z equals, because there's lots of ways to write planes. There's sort of the ax plus by plus cz equals d way, or there's the z equals stuff way. Now, the z equals stuff way is kind of convenient because when we have z equals stuff, we can read information off. Remember that our tangent plane has the following. And this is for the form z equals f of xy. So if I have z equals f of xy, what I say is that my tangent plane looks like f sub x at ab times x minus a plus f sub y at ab times y minus b plus, then there's the function at ab, which I probably should have put at the front. But what I want to point out to you is the following, that you can rewrite this as f of x ab times x plus f sub y at ab times y plus, this is a little bit technical, stuff. Now, ignoring the stuff for just a moment, what it tells you is that the coefficients for x and for y give you your partial derivatives. So that's what the point here we want to say. The coefficients for x and y gives you partial derivatives. So let's suppose we take a look at, let's start with this plane. Z equals x plus y minus 2. So we know it's tangent to the surface. We don't know where. But let's suppose we know it's tangent to the surface. Then what's true is that this 1 that's in front of the x, that's going to be our f sub x at ab. And this 1 that's in front of the y, that's our f sub y at ab, where ab is the point where the first plane is tangent to the surface. Okay. Now the question is that useful information? Well, let's take a look at our f. Here's our f of xy. What is f sub x? 2 over a times x. What's our f sub y? 2 over b times y. So, suppose we know that f sub x at ab were equal to 1, which we know. And we know that f sub y at ab were equal to 1. Well, that tells us that we can actually solve for x and y in terms of a and b. This says that x had better be equal to 1/2 a, and this tells us that y had better be equal to 1/2 b. So I now have x and y in terms of a and b. So I don't know what a and b are, but I know that that's where that plane, this first plane to that surface, that's where the tangency happens. But now let's remember one other thing. They're tangent. So if we're tangent, what must be true? Do you remember what it means to be tangent? To be tangent, think of your Latin when we were taking your Latin class, of course. I know probably some of you skipped your Latin class that day. So the word tangent means touch. So a tangent line will touch your curve. Now what does that mean? It means that at this point, this plane and this surface have to have the same z value. So let's look at what happens for that z value. So when we plug in a 1/2 a, 1/2 b into the surface z equals 1 over a x squared plus 1 over by squared, we get 1 over a times 1/2 a squared plus 1 over b times 1/2 b squared. Whoops, 1/2. The square should be there. Sorry. There we go. All right, back on track. And then equals, over here, 1/2 a plus 1/2 b minus 2. So, if we clean this up, we get a squared times 1 over a, that's a. So, and then we square the half, so that's a 4th a. Similarly, b squared, then 1 over b, that's a b, plus a 4th b. That's going to equal a 1/2 a plus a 1/2 b minus 2. Let's multiply by 4 so we can clear our denominators. A plus b has to equal 2a plus 2b minus 8. And finally we rearrange and we get that a plus b equals 8. So there's a fact. So what we know is whatever a and b are, if we add them together, they have to combine together to be 8. And that's from being the tangent to the first plane. And remember, we have two planes. So we're going to get to do this one more time. But now that we have the process down, it's a little bit easier. Now, here, when we talk about our point, it's a different point because they're not going to be tangent at the same point. So I'm going to say, well, here's this other point. F sub x at some c comma d is 4, and f sub y at c comma d is negative 2. So, but the same process works. So we get that 2 over a times x is going to equal 4. And 2 over b times y is equal to negative 2. So I'm reading the coefficients, setting them equal. So that tells us here that x is going to be equal to 2a. And y is going to be equal to negative b. Plug them in. So we're going to plug them into both the plane and the original surface. So we're going to have 1 over a times 2a squared plus 1 over b times negative b squared is going to be equal to 4 times 2a minus 2 times negative b minus 14. On our first expression, we get a 1 over a and an a squared, so that's nice. It ends up being 4a. We'll get a 1 over b and a b squared, so that's b. That's going to be equal to 8a plus 2b minus 14. And if we move stuff around, what do we end up with is we end up with 4a plus b equals 14. So now that's the second relationship that a and b have to satisfy. Well, two equations, two unknowns, our favorite kind of thing. Okay, so if we subtract the first one and we add the second one, what do we end up with? Well, 4a minus a is 3a. B minus b, gone. That's why we're combining them. 14 minus 8, 6. So that tells us that a is 2. Suppose you know a is 2. Go into your first equation. 2 plus b has to equal 8. So what is b? B is 6. So that's our choice. If you choose a equals 2 and b equals 6, then that is the case that that surface, 1/2 x squared plus 1/6 y squared, has these two planes as tangent planes. Ah, good times. I like this one. I like this one. Okay. Number 5. So another tangent plane problem. Find the tangent plane to the level surface x squared y plus 3x e to the 2z minus 4 equals 2z sine of y plus 3 at 1, negative 3, 2. Now the nice thing is we know we're looking for a plane, so we always know, well, if it's a plane, I need a point and a normal vector. So for this kind of problem, we say, okay, how do we go about it? Now there's two types of tangent plane varieties. So one type of tangent plane variety is the one we talked about in the last problem, which is this one, z equals f sub x ab, f sub y ab, so forth and so on. That's when you have z as an explicit function of f of x, y. So if you can solve for z equals f of x, y, this is the type of tangent plane you want to use. But if you can't solve for z, and as an example, you'd have a hard time solving for z here, because you see there's a z up in that exponential function, and a z down outside of the exponential function. That's tough. So you can't solve for z. So when it's this type of relationship, we say, here's how we want to think of it. This is the case where if we think of this surface as being a special type of surface, namely f of x, y, z equals to some constant k. So this is like a level surface of a higher dimensional function. Then, in that case, the normal vector is actually easy to find. Do you remember how to get it? It's the gradient. So, when we see this type of problem where it's a tangent plane and there's some sort of crazy thing we can't solve for z, the process is the following. Rewrite it in this format, which means move everything across. So we can't take the gradient yet because you'll notice that both sides have variables. You need to have all the variables on one side. So the safe thing is put everything on one side. It's okay if you leave a constant on the other side, but just have it put everything on one side. So we get x squared y plus 3x e to the 2z minus 4 minus 2z sine of y plus 3 equals 0. It's the same relationship, we've just rewritten it, so we're perfectly fine. Now we're going to think of this left-hand side as our function f of x, y, z. Take our gradient. So gradient meaning partial derivatives. Derivative with respect to x, 2xy plus 3e to the 2z minus 4. Derivative with respect to y, there's a x squared, no y in the second term. And then there's a y inside the sine, so we get minus 2z cosine y plus 3. And then the last thing with respect to z, well, there's nothing in the first term, but there is 1 in the exponent. So there's a 2 comes down, so that's 6x e to the 2z minus 4. And there's a single z there, so minus 2 times sine of y plus 3. Now this is not our gradient vector, sorry, this is our gradient, but it's not our normal vector. Not yet. What do you need to do to get to the normal vector? Plug it in. So, gradient at 1, negative 3, 2 is, now you just have to be patient, 2 times 1 times negative 3, negative 6, plus 3 times e to the 4 minus 4, that's e to the 0. Well, that's e to the 0 is 1. So it's negative 6 plus 3, comma. 1 squared, 1, minus 2 times 2, that's 4, times cosine of 0. Cosine of 0 is 1, so that's 1 minus 4. Then we get 6 times 1 times e to the 0. Well, that's 6 again. And then we have minus 2 times sine of 0. Well, sine of 0 is 0. So that's it. So we end up with minus 3, 6. All right, so there we go. There's our gradient factor. Now, on a side note, we could choose any multiple of this factor. We don't have to, but we could. The reason I point this out is sometimes it's easier to manipulate things later on. So if you see anything that's a common factor, or say you want to multiply through to get rid of fractions, you can do that. Do you see anything that's common here? The 3's. So what we'll do is we can choose our normal to be 1/3 of this. So we're going to choose our normal. Any multiple that's not 0 will work. So negative 1, 2. That's going to be an easier vector for us to work with. If you don't do that, you still get the same plane, so it's still full credit. It's just a little bit easier when you go to your next computation. So that's our normal. We're not done yet because the question asked us for a plane, so we better stop when we get to a plane. We haven't gotten to a plane yet. So, but these are our coefficients. So I can write this as minus x minus y plus 2z, our coefficients of x, y, z, equals something. All right, what's that something? Well, minus 1 minus 3, and then plus 2 times 2. So that's minus 1 plus 3 plus 4. And that looks like 6 to me. So there we go. All right. Is that right? Did it work? All right, good. Whew. I like it when it works. That's my favorite thing. All right. Number 6. Let g of x, y, z be a differentiable function. That means we can take derivatives, so it's the kind of function we like. It's the kind of function that we'd like to take home to meet our parents, because our parents would definitely approve. Okay. Now this function has a couple of interesting things. So the rate of change from the point -3, 4, -2 towards the point -3, 7, -2 is 6. The rate of change from the point -3, 4, -2 towards the point -9, 4, 6 is also 6. Oh, that's okay. The rate of change from the point -3, 4, -2 towards the point 9, 7, 2 is 6 again. All right, all right. Determine the maximum possible rate of change at the point -3, 4, -2. Well, that shouldn't be so hard. It says if we go in this direction, we get 6. If we go in this other direction, we get 6. If we go in this third direction, we get 6. Clearly, the answer is 6, right? Or is it? Maybe it's not so clear because not everywhere we're going to go is going to give us a change of 6. How do we know that? Well, maybe, but here's one way to think about it. What if I went not towards the point, but in the opposite direction from that point? What would happen to my rate of change? It would become -6. So not every direction is going to give us +6. So it's probably not that easy, which means we're going to have to work a little bit. Well, let's find out. All right. Well, maximum possible rate of change. Now, they emphasize the word maximum. That's interesting. So whenever you see the word maximum, and it's attached to the word rate of change, or if you like, derivative, and we're doing multivariable calculus, what do we think? Gradient. This is something about asking us about the gradient. So this question is a very much a gradient type of question. Do we understand the gradient? And can we understand how things work with the gradient? So we're going to think about it and say, all right, let's call our gradient at our function -3, 4, -2. We're going to call it a, b, c. And if we know what a, b, and c are, then we can say that the answer to this will be the magnitude of this vector a, b, c. So whatever that turns out to be, that's our answer. And I really hope I don't feel bad. I hope it fits in the box because that's going to look foolish if it doesn't fit. Okay. All right. Well, to begin, these are all about rates of change. And so when we're looking for a rate of change in a direction, that's also known as a directional derivative. So what's the basic procedure for finding a directional derivative? So the direction u, the directional derivative in a direction u of a function f, well, actually let's change it to g because our function is g, at a point p is going to be the gradient of g at our point p dotted with u, which in our case, our gradient is a, b, c dotted with u. So that's our directional derivative. So we need to go through and find these directions. So let's go through one by one. So the first one, let's just call this, we'll call it a. So for a, what's our vector u? Well, first off, what's the vector that goes from -3, 4, -2 towards -3, 7, -2? Well, we look at just the changes, 0, 3, 0. Is this u? No. It's wrong size. But that's okay. We can scale this. This is actually easy to scale. What's u? 0, 1, 0. So, now we apply the rule. So we say that 6, and that 6 is coming from here, is equal to a, b, c dot 0, 1, 0. Well, if we take this dot product, we get 0a plus b plus 0c. So now we know what b is. B is 6. So that's cool. We know b is 6. All right, one down. We need to find a and c. All right, so let's go to part b. The rate of change from the point -3, 4, -2 towards the point -9, 4, 6. Okay, how much do we change in the x direction? -6. In the y direction? 0. In the z direction? 8. All right. Is that our unit vector? No. Wrong length, for sure. For sure. Now, if you look at it, we can scale it to something a little bit easier to spot, because we really are just interested in the vector, the direction of the vector. It's the same direction as negative 3, 0, 4. Do you know what the length of that vector is? 5. Yeah, that one's one we see a lot. So that unit vector would be negative 3/5, comma 0, comma 4/5. So that's the right unit vector. So now we say that 6, which is now the second 6 here, is equal to A, B, C, dot with negative 3/5, 0, positive 4/5. Well, that's going to be negative 3/5 times A plus 0 plus 4/5 times C. And if you clear off your denominators, you're going to get negative 3A plus 4C equals 30. Because I can multiply both sides by 5. So that's some relationship between A and C. All right. Cool. Now we'll come to the last item, the third one. So for the last one, okay, negative 3, 4, negative 2, and 9, 7, 2. Well, how much do we change in the x direction? 12. 4 to 7, how much do we change? 3. Negative 2 to positive 2? 4. Now, this one, maybe it's not quite so clear, so we do the little computation. That's 12 squared is 144, 3 squared is 9, 4 squared is 16. If we add those up, we end up with 169, I think. Now, is the square root of 169 a nice number? 13. Wow, cool. Cool, cool, cool. So we just divide. So, I'll write the 1/13 in front. 1/13, 12, 3, 4. So, the last part, 6, is equal to, and I'm going to write this as A, and we already found B, so let me just put the B in already. 6, comma C, dot with 1/13, 12, 3, 4. So this is equal to 1/13 times 12A plus 18, 6 times 3, plus 4C. Multiply both sides by 13, we get 78 equals 12A plus 18 plus 4C. Subtract 18, we get 12A plus 4C equals 60. And for reference, I'm going to write down the negative 3A plus 4C is equal to 30. So here we have two equations. So that comes from here. Two equations. Let's just subtract. Fingers crossed, things work out. 12A subtract negative 3A. 15A. Oh, we're off the bottom. 4C subtract 4C. 0. 60 subtract 30. 30. So what's A? A is 2. Wow! That's a nice number. Somebody really planned this carefully. Okay, now we're almost there. What about B? What about C? So plug in. Say, come here. 2A, that's 24. Plus 4C equals 60. If I subtract 24 from 60, I get 36. So C is 9. So our gradient vector is the vector 2, 6, 9. So we now need to find the magnitude of 2, 6, 9. All right, well, that would be the square root of 4 plus 36 plus 81. Well, if we add those numbers up, 4 plus 36 is 40. 40 plus 81 is 121. That's 11. So our answer is the maximum possible rate of change is 11. I got to be honest with you. Of all the questions on the exam, I like this one better. This is just so cool because it's like, oh, you get 6 if you go that way, and you get 6 if you go that way, and you get 6 if you go that way. So what's the answer? 11. What? How? How? That doesn't seem possible. But the math says it. So there you go. All right. Next problem. Let f of xy equal x squared y plus 3y squared plus 4x minus 5y. Determine the rate of change of the function from the point 5, 1 in the direction of the point 2, 5. Well, that's pretty good. There's a couple things that give away what's happening. Rate of change. What's another way to say that? Well, yeah, we're going to get to, yeah, it is a gradient problem. Rate of change is derivative. Direction is direction. So it's a directional derivative, which means we need a gradient. So the directional derivative, we already did it in the last problem. It's going to be the gradient of f at p dot u. Now in our case, this is more straightforward. So we got to do our gradient, we got to do our u. Let's do our u first. Sometimes they give it to you, sometimes you have to work on it. Here they didn't give us a vector, they gave us points, but we can use the points to get a vector. So we need a vector that goes from 5, 1 to the point 2, 5. So what vector does that? -3, 4. So you just look at how much did you change in x, how much did you change in y. Make sure you understand which one is the start and which one is the end. Otherwise you'll be off by a negative sign and you'd lose a point. You don't want to lose a point. You want to get all the points. All right. As we just talked about, is this our vector? No. But what can we do? Divide by the magnitude. Now, in this particular case, the magnitude is easy, so that's -3/5 and 4/5. Okay, so we're halfway there. -3/5, 4/5. Now the gradient. Okay, so the gradient of f. What does that turn out to be? So, with respect to x, what do we get? 2xy, and then 2 plus 4. With respect to y, x squared, and anything else? -5. Now you plug it in at the point, because if you're going from a point, that's the point where you plug your gradient in, because a directional derivative should be a number. It shouldn't be a function, it should be a number. So, plug in 5, 1, and we're going to get 2 times 5 times 1, which is 10, plus 4, which makes 14. Then we're going to get 5 squared, which is 25, plus 6, but then minus 5. So that's 26. Okay, so 14, 26. You don't make this a unit vector. No. Gradient is the gradient. Okay, and then we're almost done. So that's -42 over 5, which is 14 times -3/5. Then 4 times 26 is 104 over 5. And we can finish this one. Okay, that's 62 over 5. Yeah. If you were an engineer, 12.4000. So, but we probably would say 62/5 is the better way to write that. Find partial z, partial x, partial y, and partial y, partial z. For y, z squared plus 3x e to the y minus 3z sine of 2x equals 6. Now, what is this problem? How do we know what type of problem this is? Whenever you're asked to find a derivative, you say, can I solve for z? And if the answer is no, we probably almost could here, but not really. You have to solve some crazy quadratic. If you can't solve for z, and you're asked to find a derivative with respect to z, then that means it's implicit. Now, the way that implicit works is it always works the same way. We say, I'm going to take a derivative, so I'm just going to take the derivative, but I don't know exactly how z depends on my other variables, but I know that it does. So there's 3 things. So we're going to do these each one. So one, when I'm looking at partial z, partial x, what I'm going to do is I'm going to think of it as saying, okay, the implicit relationship says that z depends in some way on x and y. I don't know how, but I know it does. So I'm going to take the derivative. Now, derivative with respect to what? Well, we read it off. See that partial x downstairs? that says we're taking the derivative with respect to x. So we're going to take the derivative with respect to x of everything. We're going to think of x and y as being the independent variables, which means that they can be whatever they want. Whatever x does is independent of what y does. But z depends on x and y in some way. So the key is whenever we come to a place where we see a z, we say, oh yeah, it depends on x and y. So taking the derivative with respect to x of both sides. Well, the y, that's a constant as far as we're concerned, but the z depends on x. So the derivative of the first term will be 2y z to the 1 times the derivative of z with respect to x, which is the derivative of z with respect to x. The next term with respect to x, well, that'll be 3 e to the y. Again, y is treated like a constant because it's independent of x. So as x changes, y doesn't do anything. Come to the last term, we have to do a product rule because there's an x inside of the z, and then there's an x where it says x. So minus 3, derivative of the first term, partial z, partial x, sine of 2x, and then minus 3z times 2 cosine 2x equals the derivative of the other side. Well, that's 0. Now at this stage, you say, all right, everything which has a partial z, partial x, you put those together and you factor it out. So you get partial z, partial x times 2yz minus 3 sine of 2x. And that's going to be equal to the stuff that you move across, because everything else moves to the other side. 6z cosine of 2x from this second term, and then minus 3e to the y. So our conclusion is that partial z, partial x is equal to 6z cosine of 2x minus 3e to the y, all divided by 2yz minus 3 sine of 2x. Okay? So that's partial z, partial x. Now, suppose we go and look at the second part of this problem, because this has, again, 3 parts. Partial x, partial y. Now the question becomes, wait, what happens here? And the answer is, it's an implicit relationship, which means that the variables depend on each other in some way. We change our mindset. So here what happens is our mindset changes. We're going to think of x as now being a function of y and z. Because just as I could say an implicit relationship defines z in terms of x and y, the exact same reasoning says x is defined in terms of y and z. If you tell me y and z are, you've told me what x is. So now I'm going to take the derivative with respect to what? Well, the reason I'm asking you the question, no. The derivative with respect to the variable y, again, because it comes from the downstairs. So we take the derivative of both sides with respect to y. Every time I see an x, I say, oh, remember that x depends on y. But now when I see z, I say, look, z is my other independent variable. There's no dependence at this stage. Essentially what I've done is I've reset, and I'm thinking of it as a whole new problem. So, do the process again. So, derivative of the first term will give us z squared. That's z is acting like a constant because we're taking derivative with respect to y. Derivative of the second term, product rule. So that's going to be 3 partial x partial y e to the y plus 3x e to the y, because the derivative of e to the y is e to the y. Then on our last term, we're going to get minus 3z times 2 cosine 2x times partial x partial y equals 0. Again, though the process is similar, you say everything with the partial x partial y, factor that out, so partial x partial y times by 3e to the y minus 6z cosine 2x equals, then you say, okay, what goes to the other side? Well, the z squared does, so that's minus z squared, and this 3x e to the y does. And so the conclusion is partial x partial y is negative z squared minus 3x e to the y divided by 3e to the y minus 6z cosine 2x. you might notice and say, hey, these are matching. Is that a coincidence? And the answer is actually no, it's not a coincidence. They should match up to some sign depending upon how you chose to mark your signs. All right, last one. Partial y, partial z. So, what happens here? Well, not a surprise. Once you get into that mindset, it says, hey, now y is going to be some function y as x of z. And we do the same thing that we do. So, we're taking the derivative with respect to what? With respect to z. And so the first one is product rule. You'll get partial y, partial z, z squared, plus y times 2z. Then the next term, well, the nice thing is the 3x is like a constant, so it's 3x, e to the y times the derivative of y with respect to z, partial y, partial z. And on the last term, we're taking the derivative with respect to z. X is a constant, so we get minus 3 sine of 2x, and that equals 0. Factor out the partial y, partial z, and you get z squared plus 3x e to the y equals, bring the other stuff across, 3 sine 2x, and then here you'll get minus 2yz. So we end up with partial y, partial z equals 3 sine of 2x minus 2yz, all divided by z squared plus 3x e to the y. And there you go. That's it. So the implicit differentiation problems are, once you recognize this implicit differentiation, it's always the same idea. Say, okay, what is my variable that depends on the other variables? That, you look upstairs. So if it's, say, partial x, partial y, x depends on y and z. If it's partial y, partial z, y depends on x and z. And then say, okay, now I know which one depends on the others. Figure out which derivative you need to take, and there you go. Bob's your uncle, as they say. Okay. Number 9. Given that z equals minus x plus 7y plus 4 is tangent to z equals g of 3x minus 2y, comma 5x plus 3y minus 7 at 1, comma 1, then find, if possible, the tangent plane to z equals g of xy at 1, comma 1. So we don't actually have our function g here. So that makes things a little bit more interesting. So we have to find our tangent plane. Now, if you're after a tangent plane, you're really after a set of information, or rather a collection of pieces of information about your function. So if I want the tangent plane to g of xy at 1, 1, I need specifically 3 things. I need to know what is g at 1, 1. I need to know what is g sub x at 1, 1. And I need to know what is g sub y at 1, 1. If I know those 3 things, then I know what the tangent plane is. Those 3 things determine the tangent plane. If I have the tangent plane, I can extract those 3 pieces of information. So that's my goal, is to figure that out. So we say, okay, well, let's take a look. Well, first thing is, let's actually plug in 1, 1. So if you plug 1, 1 into here, what do you get? Well, you get g of 3 minus 2, and comma 5 plus 3 minus 7, which if you simplify, that gets you g of 1, 1. Well, that's rather convenient. Now, why is that rather convenient? Well, remember that this is tangent to that. Here's our surface, here's our tangent plane. So, recall what we said before. Tangent means to touch. So, if I plug 1, 1 into here, that would be the same as if I plugged 1, 1 into there, due to the tangent relationship. So, negative 1 plus 7 plus 4. That's what happens when I plug in 1, 1. So the conclusion is that g of 1, comma 1 is equal to 10. That one's probably the more straightforward part. That's usually not so hard to figure out. But now we're going to get into our partial derivatives. Now you might say, hey, shouldn't that be easy? Don't we just read off partial derivatives here? No, not quite. You have to be careful. Now, it is true that this minus 1 here is the derivative with respect to x of this function. But look how many places x shows up. It shows up in 2 locations. So what we have is we have to do a chain rule. So here's what we're going to think. So we have a function 3x minus 2y and 5x plus 3y minus 7 inside of another function. In general, if you ever see a function inside of another function, you should always think a chain rule. So we have that negative 1, which is our coefficient for that x. Well, that is partial z, partial x at 1, 1. That's where that coefficient comes from. It's saying, how is z changing with respect to x at your point? So, to figure that out, we're going to come here and take the derivative with respect to x of this expression. So the way we do it is we do the chain rule. We say, okay, where does x show up? It shows in 2 places. So we're going to say, we're going to take, all right, we'll come back to this in a second. We're going to take the derivative with respect to the first slot, so that means the x slot. We leave the function the same, 3x minus 2y, 5x plus 3y minus 7. And I'm regretting that because I don't have enough space to finish writing this down. But, okay, took the derivative with respect to the first slot times the derivative with respect to x of the first slot, which is 3. Plus derivative with respect to the second slot, which we denote by y. The inside stays the same. Then I times it by the derivative of the second slot with respect to x, which is 5. So this is taking the derivative with respect to x. Now what can we do? Well, the answer is we plug in 1, 1. So at 1, 1, this will become g sub x at 1, 1, because these become 1, 1, times 3, plus g sub y at 1, 1 times 5. And again, that equals negative 1. So that tells us something about g sub x and g sub y. It doesn't tell us what it is, but it does certainly tell us there's a relationship. And that's by looking at the derivative with respect to x. Well, what else could we have done? We could have taken the derivative with respect to y. So if we do it with respect to y, what we would say is that this 7 here, that's what the function is doing with respect to y at the point 1, 1. So we take the derivative with respect to y. Now y shows up in both slots, so we have to do the chain rule. So we take the derivative with respect to the first slot. The inside parts stay the same. That's always been the case with the chain rule. The inside doesn't change. Times the derivative of the first slot with respect to y, which is negative 2. Add that, take the derivative with respect to the second slot, well, that's the g sub y. The inside parts stay the same. And times that by the derivative of the second slot with respect to y, which is 3. Now you plug in 1, 1. Again, you're going to get g sub x at 1, 1. Actually, I'll write it up here. G sub x at 1, 1. Times that by negative 2. Plus g sub y at 1, 1. Times that by 3. And that's going to give you 7. Is there a question?
Yeah, how did we come up with 3 and 5 and negative 2 and 3? Or like what we timed?
Sure. So more generally, this is how we oftentimes write these things. It's a little bit muddled here. So let me say it this way. So this function, 3x minus 2y, let's introduce 2 new variables. U equals 3x minus 2y, and v equals 5x plus 3y minus 7. So what we have is we can think of this now as g of u comma v, but really what it is g of u of x comma y, v of x comma y. So by the chain rule, the picture is g depends on these 2 variables called u and v, which both depend on x and y. And so what we're saying here is we're saying, well, the derivative of g with respect to u, but because of our convention, really, when we say the derivative of g with respect to u, it just says take the derivative with respect to the first slot. And so usually we think of it as, because we have this x here, the first slot corresponds to x. So that's why we're calling it g sub x. So that's why it's a little bit weird to say it out loud, and it's also a little bit weird to not say it out loud. But we're thinking of g sub u, which is g sub x. Okay. Then we have this partial u, partial x, and then we have this g sub u, which is g sub v, which is g sub y. Again, here the only thing that the variables indicate is which slot. Are you going with respect to the first slot or the second slot? And then you have a partial v, partial x. So if I want to take the derivative with respect to x, it's partial g, partial u, or partial x, times partial u, partial x. So partial u, partial x is 3. And similarly, partial g, partial v, which is the same as partial g sub y, times partial v, partial x, and that would be 5. So these are the partial derivatives of the inside functions, or what you're seeing.
So it's like finding the gradient. Kind of.
It's a chain rule. You want to be careful, because you don't want to... The gradient is a really awesome thing, and I don't want you to say, everything's a gradient problem. I want you to not love the gradient. The gradient should always be loved. It's a wonderful thing. But not everything has to be phrased in terms of the gradient. It's essentially saying, look at the chain rule. Think of how the variables relate to one another. So at this stage, you have now 2 equations, 2 unknowns. Good. Right number of equations and unknowns. And so, I just like to sort of scale and combine. So if I multiply, say, the first equation by 2, you get negative 2 would equal 6 g sub x at 1, 1, plus 10 g sub y at 1, 1. And if you multiply the second one by 3, 21 would equal negative 6 g sub x at 1, 1, and plus 9 g sub y at 1, 1. Let's see, did I multiply that right? That seems right. Okay. Now, what do you do? Adam, negative 2 plus 21? 19. The g sub x's cancel. 10 plus 9? It's 19. Well, what does that say about g sub y at 1, 1? It's 1. Well, that's really nice. Wow, cool. Okay, now just pick your favorite formula. Say the first one, negative 1, g sub x at 1, 1. We don't know that yet. G sub x at 1, 1 times 3, plus g sub y at 1, 1 times 5. Well, that's plus 5. So negative 6 equals g sub x at 1, 1 times 3. So g sub x at 1, 1 is negative 2. So by taking the information we have from the chain rule, we were able to figure out what's g sub x, what's g sub y at our point 1, 1, which means that we have everything we need for the tangent plane. So our tangent plane, the generic formula would be z equals g of 1, 1 plus g sub x at 1, 1 times x minus 1 plus g sub y at 1, 1 times y minus 1. So that for us becomes 10 minus 2 times x minus 1 and then plus y minus 1. And that's how we'll leave our answer. All right. Well, we've had a lot of tangent planes. Maybe time for something a little different. So given f of xy is sine of 3x plus 4y plus xy minus x squared plus 6y plus 15, use the linear approximation to f of xy at negative 4, 3 to estimate f of negative 3.98, 3.03. When you see the word linear approximation, what do you think? Linear approximation, also known as it's the tangent plane. So, again, the tangent plane again? No. The tangent plane is really important because the tangent plane It's saying what's the local behavior of the function. So we're using that to understand the function. Now, how do we know to do that? Well, first off, linear approximation should just be naturally associated with the word tangent plane. There's another key word in this problem. The other key word that I see in this problem is this word, estimate. So whenever I see the word estimate, that says I'm not after an exact value. I'm after something which is reasonably close. And the way I get something reasonably close is I say, all right, instead of figuring out what the function is, I get a tangent plane to the function at a point which is convenient for me to work with, and then say what happens to the tangent plane. So you'll notice that negative 4, 3 is very close to negative 3.98, 3.03. And negative 4 and 3 are nicer numbers to work with. So we need to get our information. So let's start building up our data. So we need to know the value of the function at negative 4, 3. Well, that'll be sine of negative 12 plus 12. And then we have x times y, which is minus 12, minus x squared, so that's minus 16, plus 6 times 3, which is plus 18, plus 15. Now, looking at this, let's see what we see. Negative 12 plus 12 is 0. Sine of 0? 0. So that's gone. That's convenient. 18 plus 15 is 33. Minus 12 and minus 16 is minus 28. Put those together, we end up with 5. So one bad approximation is 5, but that isn't using the linear approximation. That's using the constant approximation. We want to use the tangent plane, which means we need to get to f sub x and f sub y. So what is f sub x? Well, take the derivative with respect to x. 3 cosine of 3x plus 4y plus y minus 2x. And f sub y is very similar. 4 cosine of 3x plus 4y plus x plus 6. Okay, so we take our partial derivatives. What do we do with our partial derivatives once we've taken them? We plug them in. And namely, we plug in the point negative 4, 3, because that's where our linear approximation needs to be at. So f sub x at negative 4, 3. Well, we're going to get 3 times cosine. Here on the inside, we're going to get negative 12 plus 12 again, which is still 0. That's nice. Plus y, which is plus 3. And then minus 2 times x, which is minus 4, so plus 8. Well, cosine of 0, 1. So we get 3 plus 8, 14. F sub y at negative 4, 3. Well, that'll be 4 cosine, and again, that's also 0, plus x, so plus negative 4, plus 6. Well, 4 and negative 4 cancel, so we get 6. So, we're almost there. So the linear approximation is the following function. Namely, L of x is equal to f of negative 4, 3 plus f sub x at negative 4, 3 times x minus minus 4, so that's really x plus 4, plus f sub y at negative 4, 3 times y minus 3. So we put in these numbers, 5 plus 14 times x plus 4 plus 6 times y minus 3. So the function at negative 3.98, 3.03 is approximately, why did I put L of x? I am sorry, L of x comma y, excuse me. Approximately L of negative 3.98, 3.03, which is 5 plus 14 times negative 3.98 plus 4 plus 6 times 3.03 minus 3. You'll notice that when I did the linear approximation, I didn't expand and group, because oftentimes when you're going to use a linear approximation, you don't want to, because you want to focus on the changes. And if you expand, it's a lot harder to do these changes. We're almost there. Negative 3.98 plus 4. What will this give us? 0.02. 3.03 minus 3? 0.03. So we're going to get 5 plus 0.02 times 14, which is 0.28. 0.03 times 6, 0.18. 0.28 plus 0.18 is 0.46. So we are approximately at 5.46. All right. Find the second order Taylor polynomial for h of xy is log of xy plus 2x squared y plus e to the power 2x minus 3y plus 1. Now, second order Taylor polynomial means that we're going to take all our derivatives up through the second order. So this is taking lots and lots of derivatives. Well, we should be able to take lots of derivatives at some point. Remember the philosophy of Taylor polynomials. The philosophy of Taylor polynomials is to say, I am going to match all the derivatives up through some order. And in this case, we're going to match all the derivatives up through the second order. So, there's a typo on this problem. What's the typo? We didn't tell you where. At 1, 1. Okay, because you can't take a second order Taylor polynomial unless you know where. All right, so there we go. There's our location. All right, back on track. Okay, don't worry. The test has been much more thoroughly checked than the practice problems. All right, so we're going to find the second order Taylor polynomial at the point 1, 1. So we need to do a couple of things. What is the second order Taylor polynomial in general? So in general, it is the function at your point plus you take the first derivatives, h of x at ab times x minus 1, and h sub y at ab times y, well, this is y minus x minus a. I'll do the very generic one here, y minus b. So at that point, what we have is the tangent plane. So the tangent plane is a Taylor polynomial. The second order one says, hey, keep going. hxx at ab over 2 times x minus a squared. And hxy at ab times x minus a, y minus b, and hyy at ab over 2 times y minus b squared. So this last part here, these last three terms are just saying, also look at your second derivatives. So if you have a problem with Taylor polynomials where it says find the Taylor polynomials, you always do it the same way. You just sit down and take a bunch of derivatives, and then you evaluate all your derivatives, and then you plug it in. And as long as you know that you have to do that, and you know how to plug it in, the problems themselves aren't so bad. So we'll start by rewriting the function. By the way, log of xy, what's another way you can write that? You can do log x plus log y. You can pull it apart. Sometimes if you have a log, it makes it easier to work with if you pull things apart. Okay, so h sub x. Well, derivative of log x, 1 over x. Log y, 0. 2x squared y, 4xy. Derivative of e to the 2x minus 3y plus 1, 2e to the 2x minus 3y plus 1. H sub y, well, derivative of log x is 0. Derivative of log y is 1 over y plus 2x squared. How about the derivative of the last piece? E to the 2x minus 3y plus 1 will be minus 3. E to the 2x minus 3y plus 1. Okay, h sub xx. So go to h sub x, take that derivative, minus 1 over x squared plus 4y. And here, you'll get another 2 coming down. So you're up to 4. 4e to the 2x minus 3y plus 1. Now hxy, remember that the second order when we mix the derivatives, so one with respect to x, one with respect to y, it actually doesn't matter which way you take it. You could do first with respect to x, then with respect to y, or vice versa. You'll get the same answer. So if I take the derivative of the h sub x, take that derivative with respect to y, This term disappears. Derivative with respect to 4xy with respect to y will be 4x. Then here, when I take either 2x minus 3y plus 1, to take that derivative with respect to y, it's negative 6. Now, it's not a bad idea to just sort of double check and say, what happens if I took the other derivative with respect to x? If you get the same thing, then you're good. If you don't, something's happened. And, just check your work. HYY, well, negative 1 over y squared, 2x squared, gone. And then you'll bring down another negative 3, so plus 9, either 2x minus 3y plus 1. So there's our functions. Next, we evaluate. So plug in 1, 1. Log of 1 is 0, log of 1 is 0, 2 times 1, then we're going to e to the 0. So we're going to get 3. H sub x at 1, 1, 1 plus 4 plus 2, 7. H sub y at 1, 1, 1 plus 2 minus 3, 0. HXX at 1, 1, minus 1 plus 4 plus another 4, makes another 7. HXY at 1, 1, 4 minus 6, negative 2. And HYY at 1, 1 is minus 1 plus 9, which is 8. So take your derivatives, you evaluate, and now you plug everything in. So you're going to get 3, which is your h of AB, plus h sub x at AB, so that's 7, times x minus 1, plus 0 times y minus 1, so that doesn't need to write that down, plus, then the next term is the hxx over 2, so that's plus 7 halves, x minus 1 squared. Then hxy, which is negative 2, times x minus 1, y minus 1. And then plus hyy over 2, so that's 8 over 2, which is 4, y minus 1 squared. Don't expand it out. Leave it like that, and life is good. Okay. That brings us into our final set of problems, which all have a common theme. Namely, these are all about classification or maximization. They're all optimization related. So we'll start with the first one. Find and classify all critical points. So if you ever see any problem that says find and classify, this is a very straightforward process. You just have to remember the process. So first off, where are the critical points? The critical points are going to be where the gradient of your function is the 0 vector. So the find stage, you do the following. You take your partial derivatives, and you're going to set them to 0. What is g sub x? G sub x is 8xy minus 2y squared plus 14x. Oh, there's a lot of stuff here. Plus 8. Oh, that does not look very good to work with. Well, what's g sub y? Maybe that'll be better. 4x squared minus 4xy. Oh, and that's it. Oh, that's a lot easier to work with. Now, when I say easy to work with, remember, we're setting these equal to 0. Now, when you set things equal to 0, there's more or less two basic things you're looking for. And they are the following. Namely, you can look for factoring, and I strongly encourage you to look for factoring first, and substitution. The reason I say look for factoring first is if you can factor, it greatly shrinks your problem down. The other thing you can do if factoring or substitution doesn't work, think about ways to combine. But almost always factoring or substitution should work. And if your problem is not factoring and there's not a clean substitution, check your derivatives, because something should happen so that it's reasonable to work with. So between g sub x and g sub y, which one looks funner to work with? G sub y looks a lot easier. It's a smaller expression. And in fact, if you stare at it, you might notice that they have something in common. They have 4, but they also have x. So that tells us that we can factor this as 4x times x minus y equals 0, which tells us that we have two roads. There's the x equals 0 road or the x equals y road. And that's just from the G sub y. So from G sub y, we know that a critical point either has to have x equals 0 or it has to have x equals y. Suppose we go down the x equals 0 road. Now what you do is you go into the G sub x, and everywhere where you see x, you put 0, because we're on the x equals 0 case. So we're going to get 0 minus 2y squared, 0 plus 8 equals 0. If you rearrange this, this becomes y squared equals 4. What does that say about y? Plus or minus 2. That's right. Which means that we have now 2 points, 0 comma 2, because we're at x equals 0, y equals 2, and 0 comma negative 2. Okay. So that's not all our points, because that was only one route. We went down the route of x equals 0. Suppose we go down the route of x equals y. Well, if x equals y, everywhere where I see a y, I'm going to replace it with the x. So 8xy becomes 8x squared. 2y squared becomes 2x squared. And then 14x, turns out we're going to leave as 14x. Now we can clean this up. 8x squared minus 2x squared is 6x squared, then plus 14x plus 8. What can we do here? Divided by 2. So we get 3x squared plus 7x plus 4 equals 0. Now at this stage we say, boy, it would be great if this factored. Does it factor? Yeah. Like I said, you're going to leave calculus and you're like, all polynomials factor. Well, there was that one time in Calc 1 when it didn't factor, but that's just the odd one out. What does it factor as? 3x plus 4 and x plus 1. And check, 3x squared plus 3x plus 4x makes plus 7x and plus 4. So, what's true about x? Well, negative 1 or negative 4/3. So now we have two additional points. Negative 1, and negative 4/3, negative 4/3. So these points are like really close to each other if you look at them. But you know what? Even if you're really close, you can have very different behavior. And that's it for the find. So the find stage, always the same. Take your gradient, set the terms equal to 0, you get a system of equations. And I'm going to emphasize, you only ever do this when you have a function of two variables. You never do this for functions of three variables. So you have two equations, two unknowns, and just work the problem. Rearrange, solve for your x and y. And you're going to get a series of points. You're not going to have to do anything more complicated than what we've just done. Probably you're going to have to do something less complicated if this ends up being a type of problem on the exam. Okay, but we're not done, because the problem continues with the classify. So when we talk about classify, the classify is when we go and use that D. That's fxx, fyy, minus fxy squared. And there were a couple possibilities. If D is negative, what's true? It's a saddle. If D is positive, well, then you have to split into two cases. If fxx is also positive, what do we have? It's a local min. And if fxx is negative, a local max. This follows the same pattern that you saw in Calc 1 for the second derivative test. Finally, if d equals 0, what do? You say inconclusive and you stop. You don't have to go any further. If that happens, you just say inconclusive and we're not going to go any further. So don't have to try anything else. All right, well, so we got to find the second order derivative. So that's cool. Cool. So g sub xx, what does that turn out to be? Well, 8y, I don't know why I needed a parenthesis, 8y and 14. G sub yy, negative 4x. G sub xy, well, take derivative with respect to y in the first line. We'll get 8x and minus 4y. And that's all we'll get. Okay, so our discriminant d is equal to 8y plus 14 times negative 4x. Then we're going to subtract 8x minus 4y quantity squared. All right, so we have to plug in each one of these 4 points into this expression. Now the good news is some of these are going to be really easy to plug in. Notice the first point. When we plug it in, we get x equals 0, which means that x there knocks all of that out. And then it's 0 minus stuff. And it turns out that that stuff is going to be, because x equals 0, it's going to be 64, negative 64. So d of 0, 2 is negative 64. It's very, because that makes it simple. So what does that say about this point 0, 2? Saddle. Okay, if you plug in 0, negative 2, the same thing happens. Again, the 0 for x knocks out the first term. That term is gone. Plus minus doesn't matter after you square it. So this is also the same as d of 0, comma, negative 2. So what's true about 0, negative 2? Still a saddle. All right. Well, 2 to go. 2 down, 2 to go. Negative 1, negative 1. Well, plug that in. Let's see, what do we get? d of minus 1 will be minus 8 plus 14 is 6. Minus 4 times minus 1 is 4. Then we're going to subtract 8, negative 8 minus negative 4. Okay, so that's, all right, negative 4 squared. So we're going to subtract 16. Yes? No? So what does that turn out to be? 8. Do I care that it's 8? No, not so much. What do I care? Positive. So what does that tell us? Tells us it's something. It's a local min or a local max. But to figure that out, what do we do? Look at either fxx or fyy. In that case, what do we see? We see positive, because 6 is positive, 4 is positive. So our conclusion is that negative 1 is a local min. All right, now, negative 4/3, negative 4/3. We're right next to a local min. Maybe it's even local minier. No, I don't think that's a word. Okay. D of negative 4/3, negative 4/3. Okay, well, what do we get? Negative 4/3 times 8 is negative 32/3. 14 is 42/3. Put those together, we get 10/3. Negative 4 times negative 4/3 would be 16/3. Then we're going to subtract. Now we have to do that. Let's see, 8, that'll be negative 32/3 plus 16/3. So that's going to be 16/3 squared when we work it out. Well, what's bigger, 160/3 or 169ths or 256/9? Or rather, should we say, is it positive or negative? It's negative. Even if you don't know what the number is, as long as you know the sign, that's all we care about. So what's true about negative 4/3? Negative 4/3? Saddle. All right. Saddle. Good. Number 13. Let R be the region bounded by the lines y equals 0, x equals 0, and y equals minus x squared plus 2x plus 3, with corners at 0, 0, 0, 3, and 3, 0 shown below. Determine the minimum and maximum values of f of xy, which is x squared minus 2x plus y squared minus 4y plus 3 on R. So this is a absolute max and absolute min. Well, it doesn't use the word absolute, but it is. I mean, we want to find the largest and smallest values. So how do we go about this problem? What's the procedure? What? Okay, all right. I was hoping someone was going to break into song. We're making a list, we're checking it. No, all right, that's fine. So yeah, so someone said check the interior, but what we're looking for is we're saying, look, we know there's a max and a min. There has to be, because this is a nice function. Where's our function? There it is. It's a nice function, and we're on a closed and bounded set. So we have to attain a max and min. So we're going to make a list of all the places where a max or min could occur. What should you always throw into your list just to make sure you don't forget them? Yeah, you always throw the corners in. And you know, when you throw in the corners, it's like, I'm making progress. I'm contributing to the solution. Plus, you know, you get a point. Usually we know it's like a point. They check the corners. Okay. But now we have sort of two places. One is the inside, and then one is the edge. For the inside, that's where we look for the gradient. So we set our gradient equal to 0, which means we set our partial derivatives equal to 0. What's f sub x? 2x minus 2. We're going to set that equal to 0. F sub y? 2y minus 4. Set that equal to 0. And now we have a system of equations we have to solve for x and y. I think we can do this one. What's true about x? X equals 1. What's true about y? 2. Now, before we add it to our list, we always come and check 1, 2, is it in our region? It is. If it's in our region, we add it. If it's not in our region, forget it. We don't want that kind of thing. Okay, so now we've checked the interior. All the interior points except that one we've thrown out. Now comes the fun part. Or, if you like, the long, tedious part. It's about the same thing. Okay, we look on the boundary. Now in this case, we have 3 pieces of boundary, which means we're going to get to do 3 problems. So we have the bottom side, the left side, or the parabola side. Which one do you want to do first? Bottom side. What's true about things on the bottom? Y equals 0. See, our goal here is to get down to a single variable. It says on the bottom, you might as well treat y as 0. So our function really says, I'm on the function f of x comma 0. So that becomes x squared minus 2x plus 3. We take our derivative and we say, okay, what's the root of x squared minus 2x minus 3? That's 2x minus 2. We set it equal to 0, which tells us that we still have x equals 1. So that x equals 1 on the boundary side would be a critical point. Now we check, it is indeed still in the region. If we had gotten a critical point over here, we would have ignored it. But we didn't get a critical point over there, we got a critical point there. So we add it. So 1, 0. All right, what's next? Left. X equals 0. Again, we want to get down to a function of a single variable, f of 0, y. So we plug in, everywhere we see x, we put 0. We'll get y squared minus 4y plus 3. Take your derivative, 2y minus 4 equals 0, y equals 2. It says you should pay attention to that point. So that's indeed is a point in our region, so 0, 2. All right, anything else? Well, the parabola side. Now how do we do the parabola side? Yeah, what we can do is we can replace y by this expression. So it becomes f of x comma minus x squared plus 2x plus 3. That might be a little bit longer to write that one out. Let's see what that becomes. So we're going to get x squared minus 2x plus minus x squared plus 2x plus 3 squared. This is making me nervous. Minus 4 times minus x squared plus 2x plus 3 plus 3. All right. How bad could this be? And other famous last words. Okay. Well, what do? We what? Cry? No, we don't cry. There's no crying in calculus. So, and neither do you say, well, I can drop one. That's not the attitude to have. We like, no, we're going to forge ahead. Okay, all right. So forging ahead. Well, here we go. X squared minus 2x. If we actually square this out. Let's see, do you want to square this out? Yeah, let's square it out. Now, I'm going to point out to something that we can do in just a minute here. But if you square this out, this is, it's not very hard to go ahead and just multiply this all out. It's pretty straightforward, no surprises. Okay, so that's the squared out term plus 4x squared minus 8x minus 12 plus 3. So we get x to the fourth minus 4x cubed. And I'm going to show you a different way to think about this problem in a second. So 4x squared plus 4x squared, that's 8x squared, plus x squared is 9x squared, minus 6x squared leaves us with 3x squared, minus 2x plus 12x minus 8x. Well, that'll be plus 2x at the end. And then plus 9 plus 3 minus 12 is 0. All right? So there's our f. What do we do next? Take a derivative. Okay, 4x cubed minus 12x squared plus 6x plus 2. Huh. See, this is not the way I was originally going to do it, but okay. We keep going. Do you see any nice things we can do? Well, we can divide out by a 2. That's something nice.
Factor by grouping.
Factor by grouping? We probably can do that.
You might have 2 from the left side, not the right side.
Say what? No? Okay, never mind. It's out of my mind. See anything that we can do? Okay, there is actually something you can do. When you're faced with a cubic and you don't know what else to do, you guess. What's a good guess? 1 is a great guess. Notice what happens when you plug in 1. You get 2 minus 6 plus 3 plus 1, which is 0. Which means 1's a root. Which means that this is x minus 1 times something. You can actually figure out kind of what it has to be. It's 2x squared. This has to be minus 1. The reason it's 2x squared is you got to get a 2x cubed. The reason it's a minus 1 is you have to get a plus 1. And now you have to say, well, what's the other term? Well, you have a minus 2x squared. And here, you're going to have to end up with a minus x squared. So this means you have to get a minus 4x there. So you get minus 4x squared minus 2x squared gets you minus 6x squared. And 2x squared minus 4x minus 1, does that factor? I actually don't know. Like I said, I didn't do the problem this way. It makes me wish I hadn't gone down this rabbit hole. The answer is no, it doesn't factor. So, what do we do? Quadratic equation. By the way, x equals 1 says we care about that point. So, all that work was to get us to say that 1 comma 4 is on our list. Okay, but to be completely systematic, we do the quadratic formula. Okay, 2x squared minus 4x minus 1 equals 0. I promise there's an easier way to do this. X would be equal 4 plus or minus the square root of 16 plus 4 all over 4, which is 1 plus or minus, that's 1/2 square root of 5. Now, you don't know much about square root of 5, but I can tell you square root of 5 is a little bit bigger than 2. So this is 1 plus or minus 1 point something something.
Is it 16 plus 8? Am I remembering the quadratic formula?
Oh, sure. 16 plus 8. Square root of 24 is... There's a 6. Okay. So 1 plus or minus 1 point something. Now the good news is you get a point over here, which we don't have to care about. Woohoo! Now you might say, isn't there going to be a point over here? Well, hold on, let's see. Square root of 6. What is true about square root of 6? Yeah. So there's going to be like a point here. Okay, let's pretend like we don't have to worry about that point. We're going to skip that point for now. Let's make this our list, in the interest of time, because we still have one more problem, and I want to get to that problem. We plug these points in, so you make a list. Function at 0, 0 is 3. Function at 0, 3 turns out to be something. Function at 0, 3 I think is 0. Is that, am I close? Yeah. Function at 3 comma 0 is 6. Function at 1 comma 2, 1 minus 2 is negative 1, plus 4 minus 8, negative 4, plus 3. So that's 3 minus 6. Okay, I probably should write stuff down instead of just doing it out loud. So the first part, x squared minus 2x, is negative 1. The second part, that's 4 minus 8 is negative 4. So that's negative 5 plus 3 is negative 2. F of 1 comma 0 is 1 minus 2 plus 3. So that's 2. F of 0 comma 2. That's 4 minus 8 plus 3, negative 1. F of 1 comma 4. Well, that'll be 1 minus 2 is negative 1. Then plus 16 minus 16 plus 3. So that's 2. So now we scan our list and we say, what's the smallest number on our list? Negative 2. So the smallest number is your min. What's the largest number on our list? 6. That's our max. We'll come back to that. No, we won't. There's a better way to do that problem. But I'm not going to talk about it. Because we have to talk about this one. Find the maximum and minimum values of f of xy equals xy, given that x squared minus 4x plus 9y squared equals 30. Now, some of you might say, I don't think we know how to do this one yet, but that's because you're going to learn it on Monday. Or you're going to learn it right now. So it turns out this is a problem called the Lagrange optimization, Lagrange multiplier, but it's really a nice idea. Anytime you have a constraint, so this is optimization with constraint. And here's how you do the problem. This function right here, we're going to call it g of xy. It's of the form g of xy equals some constant k. And what has to be true is that at your optimum, the gradient of f has to be equal to some multiple of the gradient of g. So in other words, these two gradients have to be parallel to each other. And that's the key. And once you understand that, everything else is really clean and fast about this problem. So there's one other good thing to remember. And here's the mantra. So if you can remember this formula plus the following mantra. When in doubt, solve for lambda. That's it. If you can remember those two things, life is good. So let's show you an example of how this goes. So we're going to set up a system of equations to find our optimum values. So we're going to look at the derivative. So this gradient of f equals lambda gradient g says f sub x equals lambda g sub x, and f sub y equals lambda g sub y. In our case, what is f sub x? What is f sub x? Well, I'm asking the question. You know. Yeah. Y equals lambda. What is g sub x? 2x minus 4y. What's f sub y? X. That has to equal lambda times g sub y, which is minus 4x plus 18y. All right? So that's our constraint. Now what happens is that this is going to give you information about x and y. And you're going to get two pieces of information. The first piece of information is right here. So this is your first piece of information. Your second piece is going to come from here. But remember, we have our mantra. When in doubt, solve for lambda. So we get that lambda is equal to y over 2x minus 4y. But lambda is also equal to x over negative 4x plus 18y. Cross multiply. Y times negative 4x plus 18y has to equal x times 2x minus 4y. Or, multiplying this out, negative 4xy plus 18y squared equals 2x squared minus 4xy. Now, if you stare at this, you'll see that something nice happens. What happens? 4xy's cancel. So, and if we divide by 2, we get that our relationship from the fact that these are going to be parallel, that x squared has to equal 9y squared. Or, two possibilities. X is 3y, x is negative 3y. Now, that's a relationship between x and y, but remember we also had our constraint. So let's suppose we go with the x equals 3y. So everywhere I see x, I'm going to put 3y. So that gives us 3y squared minus 4 times 3y times y plus 9y squared equals 30. Okay, so we're in the x equals 3y phase. So that's 9y squared minus 12y squared plus 9y squared equals 30. 9 plus 9 minus 12. 6. 6y squared equals 30. So y squared should equal 5. So what is y? Plus or minus root 5. So we say, okay, that's y. What is x? Well, x is 3 times y. So what we get is we get a set of points. So we get 3 square root of 5, comma, 3 square root of 5. Sorry, just square root of 5. So y equals square root of 5, x is 3 times as large. Or minus 3 square root of 5, comma, minus square root of 5. Now that's if x equals 3y. If we do the other case, x equals negative 3y, you'll see something similar happen. The biggest change is that it becomes minus 4 times minus 3y times y plus 9y squared equals 30, which becomes 9y squared plus 12y squared plus 9y squared equals 30. Well, that becomes 30y squared equals 30. So what is y? Plus or minus 1. Which gets you another pair of points. Namely, if y equals 1, x is negative 3. And if y is negative 1, x is positive 3. So, from the constraint, combined together with this solve for lambda condition, you get a set of points. Now, we're looking for the max and min. So what do? You plug these in to the function. The max or min has to occur at one of these. If I plug in 3 times negative 1, 3 and negative 1, I'll get 3 times negative 1, which is negative 3. This also gives me negative 3. If I plug in 3 root 5 and root 5, I'll get 3 times 5, which is 15. So the answer is that the max is 15, and the min is negative 3. So that's how these problems are done. And we'll talk more about that in class on Monday, but for now, that's it. Here we go, back to this one. So you might notice something here about this function. F of xy equals x squared minus 2x plus y squared minus 4y plus 3. On the curve, y equals minus x squared plus 2x plus 3. Well, wait a second. You have something really close here. X squared minus 2x. So it turns out that on this curve, x squared minus 2x is equal to, if you rearrange this, 3 minus y. So what we can say is on the parabola, this becomes the following, namely 3 minus y plus y squared minus 4y plus 3. Or y squared then minus 5y plus 6. So take the derivative. And what do you get? Well, you'll get 2y minus 5 equals 0, or y equals 5 halves. So if you say y equals 5 halves, where does that fit in? It fits in roughly here, 2.5. Well, okay, our point was slightly off. All right. So now what happens, how do we find it when we evaluate? Again, we can use that this is the function on the parabola. So at the point of something complicated, 5 halves, which is easy, we get the following. We get 5 halves squared minus 5 times 5 halves plus 6. Well, that's 25 over 4 minus 25 over 2 plus 6. If you put everything as over 4, you get 25 over 4 minus 50 over 4 plus 24 over 4, which is 49 over 4 minus 50 over 4 is negative 1/4. Well, that's certainly not going to be our min or our max. So that's the point. Now you might say, hold on, wait a second, I object to this method. Well, why? You only found that point. What about that point? How did we lose it? Good question. Okay. So here's where you have to be careful. You see, it is true that it's y squared minus 5y plus 6, but there's a constraint on y. The largest value of y is 3. So it's a constrained optimization. So we know that 0 is less than or equal to y, less than or equal to 3. And so you have to include the endpoints, which is why you'd also have to include that point as well. So yeah, so this is the right answer. That's good to know. Whew, good. Now we're really done. We've done it all.